So hello guys, this is Merlin and today I'll be explaining A-star search, finding the optimal path. A concise walkthrough of A-star search, constructing a sample graph, running the algorithm step by step and understanding why admissible heuristics guarantee optimal results in practical systems. So as we can see, the anatomy of a navigation graph elements for example. So S is the start node, A, and then we go to B, C, D and G. So from S, G of 0 is the initial node and G is our goal node. So as we can see, this is a summary table of a graph and there are 7 nodes S, A, B, C, D and G and heuristics. G is when discovered, H stands for heuristic and a function F is equal to G plus H. As we can see, the A-star algorithm's core principle is that it combines G of n, H of n and F of n. G of n describes exact cost from start n and f of n is equal to g of n plus h of n, priority value for expansion. Always expand the node with lowest f of n from the open set to the queue. Next, we move on to the step-by-step A-star on our graph. So we are starting with the S node. And as we expand S, G stands for 0, H is equal to 7. And then we explore B. We explore B, discover B. With that, G is equal to 5 and H is equal to 2. And then we visit D and finally we reach the goal state where G is equal to 9 and H heuristic function is equal to 0. Next, why admissible heuristics matter. Definition: admissible heuristics never overestimates true cost to goal. This ensures A-star cannot be misled into discarding an optimal path. Next, we can go to the consistency, monotonicity, efficiency booster. A heuristic is consistent if for every edge, h of n is less than a cost of n comma n dash plus hn. Consistency implies admissibility and prevents reopening nodes. Once a node is expanded, its best path is final. So benefit is it reduces reprocessing and simplifies implementation. When to prefer, use consistent heuristics in large graphs and perform sensitive systems. Practical applications and significance, we can use it in routing in Google Maps, dynamic edge weights, traffic, plus admissible heuristics for optimal routes. Robotics, we can use it where the robots are aware of the obstacle in the path, and then games and simulations, NPC movements, and stuff like that. Next, optimality, heuristics and trade-off. Optimality guarantee: with an admissible heuristic, A star will return a shortest path. If the shortest path exists, then A star will return one. Then heuristic accuracy, more informed, larger but still admissible. H is equal to fewer expansions. Overestimating H breaks optimality. So what are the takeaways from our today's presentation is that we understood what A-star search algorithm means, and then A-star balances known cost and estimated future cost via f of n function, which is equal to g of n plus h of n. And then we learned to design heuristics, craft admissible, preferably consistent heuristics for efficient optimal searches. And then we are applying that A-star search in routing, robotics, games, and logistics. So that's it. Thank you.